So good evening. Yeah, we're going to talk a little bit about olives. Some of my co-authors are sitting in the room. I already want to recognize them. Hopefully we'll have time at the end to give them a little bit more credit again. The motivation is this. We have, in the last 20 years, a big influx of modernized, intensive cultivation of olives, both for table olives and for oil in desert conditions. Good quality oil, fairly good yields, and what really typifies these areas is a lack of water scarcity, a lack of water, and the available water for irrigation is very high in salts. So we're talking 4 to 5 decisiemens per meter for irrigated crop that with a lot of water requirement because of the dryness of this area. So we're interested in what happens over time with the salinity. To understand the root zone salinity that happens because of irrigation, we need to look both at the salinity of the irrigation water coming in. So the salinity of the irrigation water that we're starting with, as the salinity is higher, of course, root zone salinity is going to be higher. But we also have to consider leaching, because farmer can manage the salts in the root zone by irrigating more and minimizing the amount of concentration or buildup of salts on the root zone, because we understand that water from irrigation travels to the roots. Most of it's taken up, transpired. Salts that come with that water travel to the roots, and most of them stop and don't get into the root itself. As those salts build up, the osmotic problems increase in advance, so leaching is a big part of it. So we have to look both at irrigation water salinity and at leaching levels in order to understand what's going on in the root zone. We're using lysimeters, big ones. These are 2.5 cubic meter weighing drainage lysimeters. They enable us to do a couple different things. First of all, we close water. Yeah, that didn't work. First, they enable us to close the water and solute balances in the system and be able to evaluate evapotranspiration or transpiration at any given time or continuously. And secondly, they enable us to have a near to field conditions with a real real soil profile with conditions that we can control, and with the ability to isolate variables and do very precise research on them, but on trees that essentially can be full-size, mature, bearing trees. So what we did was we set out to study whole tree response of bearing olives to irrigation water salinity, and on the side we tried to advance our understanding of the role of roots in salt stress responses or tolerance mechanisms. Essentially, we have two experiments going with 9 treatments. The first one being 5 levels of irrigation salt concentration or salinity levels, going from very low to very high salinity, with our mid-level being close to what our growers are using in this area, but very high salinity, based on sodium chloride. And secondly, and those are all at 1 leaching level. And then secondly, we have at 1 irrigation water salinity level, 5 leaching. And one of those is common, meaning that we have 2 experiments with 5 treatments. We really have 9 treatments across the board. Barnea olives, 4 years of growth, 3 years of experiment, and including 2 years where we were getting olive yields out of the thing. We were initially looking at tree scale, water balance, solute balance, yield response. Also looking at both full tree and leaf scale physiology. And today I'm going to talk about what we looked at in roots, which include Minirhizotron work with sampling and scanning, some microscope work, and at the end of the experiment, removal and excavation of roots throughout the profile. So just a slide and a half about how I'm going to show this data, because what we did was found a relationship between the water coming out, the drainage water coming through the root zone and its salinity, and soil solution salinity, or saturated paste salinity from soil samples that we have. And once we establish this relationship over time, we could use the drainage water salinity as an analog for soil profile salinity. So we could come up by looking at the drainage water, by having the irrigation water being a constant salinity, by watching the salinity of the drainage water, we're able to calculate profile averaged soil water salinity. Then, as we looked over time, we were able to then take that and have a time averaged profile average salinity, which means we can have a single number of what we call ECE here, or the saturated paste salinity, that represents each individual tree or each individual treatment. Right, meaning that then we can, each of these treatments have defined as soil or an average soil salinity that the trees were seeing. And then we can do things like this. We can use that number as our variable of interest, and then look at whatever we're looking at as a function of that salinity. So in this case, we're seeing 3 years of evapotranspiration per tree on a tree scale, and we get a response curve to salinity that we see that all these points, not matter what the source of salinity was, whether it was the input water or the kind of leaching that we were doing, they're sitting on a single response curve. Now, these are the other kinds of full tree, and these two representing a couple of biomass characteristics or measurements that we're doing. On the left side is cross-sectional area of the trunk at the end of the experiment. On the right side is the biomass production when we took these trees down, and that's total biomass production. So that's trunks, leaves, fruits over the seasons, pruning material and roots after we did it, and we get these total response curves that look very, first of all, similar to what we saw in the evapotranspiration, second of all, similar to one another, with a fairly steep response at the beginning of the salinity. So although we realize that our growers are growing olives under salty conditions, that they do respond, and if they had less salty conditions, then probably at least their biomass was going to be better. But let's get to roots. So when we look at roots, we see also that we're able to get a single kind of curve representing the response of roots to our root zone average salinity. On top, we're seeing the biomass from the excavations at the end of the experiment. On the bottom, we're seeing the calculation of total root area from Minirhizotron data for the whole profile of the things. And what's noticeable here is that initial response to salt at the lower end of the salinity is even steeper than what we were seeing for the full tree or the above ground. And just to demonstrate that, here I've normalized the root salinity response to above ground salinity response for biomass, and we can very, very clearly see that the roots are acting much more sensitive to salts than the above ground part of the tree is. So something's happening there at the roots. One of the things that we looked at that can give us a little bit of insight over what's happening is the amount of uptake or concentration of the sodium and the chloride, the problematic salts in the system, as a function of the increasing salinity. And here we see that across the board we see increasing concentrations of these ions as a function of increasing salinity. But the most interesting thing is that the highest levels are the first order of the youngest roots. So we're not seeing any accumulation of the salts at all. On the contrary, we're seeing the highest concentrations in the youngest roots, and we don't see that continuing as you get into oldest roots. We see it even more drastically when we compare that with the leaf levels of the same minerals. So what we have is even a very little, if any, movement of these problematic salts from the roots into the tree, up to the aerial parts, into the canopy anyway, and an order of magnitude less at the high salinity levels of the sodium and the chloride in the system. The next thing that the Minirhizotron data can show us is a number of things. Very strong response that we can see of as we increase salinity of lower root count, higher or larger diameter of roots, lower root density, and calculated lower root area that we saw earlier as a function of increasing salinity. We also use the Minirhizotron data to look at root turnover. So when we see pairs of pictures at two different times, and we use a system of colors that are representing the ages of these roots, with white roots being the youngest and light brown roots being a little older and dark brown roots being older and black roots being dead or dying roots over time. Then we can see the root turnover, or in this case, we see two different dates with the total amount of roots, and then them divided into these four different categories, or three, I think we see in the figure here. And then we can see changes over time with the increased amount of the older roots. To do it, when I normalize this picture and we can look at it this way, we see the decrease in the youngest roots, or the white roots, as a function of increased salinity, with that decrease being larger over time, and the opposite picture with the older or dying roots or dead roots, with them increasing as a function of salinity and increasing over time. So a bigger turnover, more mortality as a function of salinity. A little bit about morphology. We see the same kind of trend in increased root diameter as a function of increased salinity, reinforcing what we saw with the Minirhizotron data, and a decrease in specific length of roots, again as a function of the salinity. When we did some sectioning and looking at anatomical elements of these roots, here we see low salinity on the left and high salinity on the right. And most of you see things in roots better than I do, and already are seeing these differences in the different aspects of the roots. But just to summarize these as well, we see a decrease in the area of the tracheal vessels in the vascular cylinder as salinity increases. We see an increase in the cortex length. That's a function of number of cells, not the size of cells. And we see a decrease in xylem vessel area, and that's both vessel number and vessel size, that are happening as a function of increasing salinity. And I'm going to finish up with conclusions. What I'm going to try to do, and here I want your feedback because I may be really off, but what I want to do is try to look at what this tells us maybe about response or tolerance mechanisms to salinity for olives. So first of all, the ionic component of salt stress appears to be prevailing and strong force restricting root growth, lifespan, and development in olives. The restricted ion transport for roots to shoots protected the trees from toxicity, but there seems to be a very high cost as root growth decreased and mortality rate increased for this to somehow happen. The senescence itself may well be part of the strategy for salt exclusion and disposal. I'm not completely confident about what's cause and effect here, but I found it interesting. The salinity was shown to influence root density, longevity, morphology, and anatomy. The alterations in xylem structure, right, the fewer, smaller vessels, are likely to impair hydraulic conductivity and hence limit water uptake. And we saw this as a result of the exposure to salinity. But this may well be evolutionarily beneficial as a mechanism to reduce risk of cavitation. So I just want to again recognize the co-authors and the people involved with running the experiment. and students who were here, and the people and places and organizations who funded it, and especially you for your patience and time today. Thank you.